fun.
Nowadays, nearly everything we do can be improved with artificial intelligence. Whether you're playing a board game such as chess or driving a car, there will almost always be some form of artificial method out there that is capable of significantly outperforming you. AI started with simple logic statements, such as the if statement. If certain conditions were met, a preset response would comment. For example, by using this method, we could detect the digit 7 by detecting two near perpendicular lines. However, this requires manually defining those two lines and will fail when the image deviates by even slightly, with horrible error tolerance. Imagine going over this process for a self-driving car. To know where to drive, you would have to account for all of the traffic signs, pedestrians, and find a way to work with more digital images. It's almost impossible and definitely not worth the time. This is why today our topic is on artificial neural networks, a method that allows us to create an artificial brain to learn on its own. We will cover how to optimize them using 4 different algorithms that we recreated from scratch, as well as a method that we invented.
To understand these optimizers, we must first take a look at the basics of neural networks. A neural network has three different types of layers: an input layer, an output layer, and hidden layers. These layers are made up of neurons, which form a network of connected nodes. All of these connections are then weighted. You can think of weights as the strength of the connections between the output of a neuron to the input of another. Your job is to form associations, allowing for learning and pattern recognition. We will be training our neural network to recognize digits from 0 to 9, so our dataset consists of 28 by 28 images, each pixel being a value between 0 and 1 for black and 0 for white. We would also have a digit from 0 to 9, which would represent which image was drawn, or which number.
Let's take a look at a single neuron of a training input. After the input is formatted, it is passed into an activation function along with the allocated, initially randomized weights. This function returns the output of the neuron. The function we will be using is called sigmoid. It simply takes an x, the sum of the products of the inputs and weights, and returns 1 over 1 plus e to the power of negative x. The value returned is called the activation and can be expressed as these lines on our neural network. The higher or greener the activation, the more those neurons are relevant to each other. This process is done for each neuron in each layer until the output layer is finally reached.
Finally, when the network outputs a list of values representing its certainty of each digit's classification, its cost is evaluated by a cost function, a function that takes in the network's outputs as well as the correct outputs and evaluates how much off the neural network is performed. By subtracting the correct outputs from the actual outputs and squaring them, it would calculate the cost for each neuron. Then it sums this list of cost values to form the final cost value of the layer as a whole.
To minimize this error, we can use backpropagation. Backpropagation is a method in which each layer of weight, starting from the last layer going back to the first, gets their element change in a way that minimizes the error.
To optimize a layer of weights, we use a neural network optimizer. An optimizer takes the weights of a layer and would nudge each weight one by one depending on its effect on the layer's cost. The optimizer will correct the hidden layers one at a time, starting with the last one and ending with the first.
Gradient descent is the simplest way to do this. It first finds the gradient of the function. The gradient can be thought of as the derivative of the function. To find it, we can change a singular weight by an extremely small amount like 0.001. Anyways, after we perform this small change to a single weight, we run the last layer of the network again to receive the new cost, which we then subtract from the cost of the previous weights and divide by 0.001 again to tune it up. Finally, we subtract the gradient from the original weight we changed. This gives us the negative of the gradient, which is a step towards the cost local minimum. After a weight is changed, the next weight in the list of weights goes through the same process. This goes on and on and on and on until every single weight in the network is optimized. Here's a quick demo of it finding the local minimum of the function y equals x squared. We ran this optimizer until it got 5 decimal places within the range of the minimum. We can see that it is able to find the minima in less than a second in 21 iterations. And this is what it looks like. But of course, we can't compare to anything just yet.
Next up, we have momentum, an optimizer that takes the gradient of the cost function just like gradient descent does, with a small addition to the gradient. If you think of the corrections made by the optimizer as movement, then you can think of momentum as an optimizer that carries over that movement. Momentum starts with no velocity, then begins to move towards the local minima as usual using gradient descent, but this time with added movement due to velocity. If we were to just always add velocity, though, it would never slow down, so a hyperparameter controlling its decay is implemented, so it only carries over a portion of the velocity. This decay is called beta, a value that is optimally 0.9. Setting it too low can slow it down significantly, and setting it too high can make it jump over the minimum. Overall, momentum is a significantly faster alternative to gradient descent, although due to its added velocity, its spikes are larger and it can miss the local minima.
Nesterol, our next optimizer, is a toned down version of momentum. It simply prevents momentum from bouncing over the minimum. It does this through passing in weights minus velocity instead of the weights itself into the momentum algorithm. Although it doesn't fully get rid of bouncing, it typically makes some smaller jumps when compared to momentum. You can see that happening over here, where it is way less than momentum's jump.
NADM, also known as Nesterov Accelerated Adaptive Moment Estimation, is probably one of the best neural network optimizers currently available. It is faster than momentum and can reach the local minima with significantly less large spikes. NADM is a modification to momentum. It works by calculating the output of momentum twice to accelerate it quicker and bounce less. It does this by subtracting the sum of the velocity decay multiplied by velocity and the gradient multiplied by the learning rate. And compared with other optimizers, it reaches the local minima the fastest with higher accuracy.
Finally, to conclude neural network optimization, we have a method that we invented to counteract the bouncing effect many successful optimizers such as Momentum have. As you can see here, this is the momentum function. The main concept behind our optimizer was to control the velocity's decay, beta, relative to the change in velocity. Optimally, since beta controls the velocity, we can increase it when it's away from the minimum and decrease it as it gets closer to be even more accurate and prevent these jumps. We can predict when the function is nearing the minimum by looking at the difference between the velocity and the previous velocity. The higher delta velocity is, the more we can raise the decay. The lower it is, the more we can decrease it. We tried multiple different equations with this idea in mind. Many of them worked well on quadratic functions but failed to harmonize with neural networks. Finally, we came up with the final form of our algorithm, as you could see here.
Our optimizer first finds the delta velocity, as previously mentioned. We then use the tanh function to limit its range to between -1 and 1. This prevents the velocity decay from being too low or too high. Then we multiply it by a scale value called alpha, which is simply the maximum and minimum value we want beta to reach. We can then translate this value with beta by subtracting it, after which we multiply it with our velocity, forming the new iteration's velocity. We then add this velocity to the gradient and subtract it from the weight just like NADM, and through testing we found that the optimal value for alpha is approximately beta divided by 10. From this graph, we can see that our model completely destroys the competition in a quadratic test and thanks to its more controlled stability. However, our downside to our optimizer is that it requires more variables and mathematical operations, which barely makes a difference.
To see the true difference in our optimizers, we can use the matplotlib library to interactively plot these results. And as you can see here, debounce gets rid of bouncing by being more stable, and unlike momentum, it becomes slower as it descends, and you can actually see here how it's slightly above NADM, but it still beats it in the long run.
Finally, here are the final scores of our optimizer after training it on digit recognition for 9 hours. This short amount of training allows us to better see the difference in performance between the optimizers. It's still hard to see much from this graph though, so we will test each optimizer against each other on actual digit recognition, while we answer any questions you may have.
Alright, this is the digit recognition. And we can run this in the background for a while. Initially, you can see how Nadum is somewhat ahead of Debounce. That is because we only showed a few images, and eventually, as you can see here, Debounce overthrows Nadum, and actually, soon, probably one more iteration later, beats it. Oh, and this is the number it is guessing, and how certain it is, and the overall score it receives. We believe that Momentum and Nestral missed the local minima a lot. That's most likely the reason they seem completely random. At least Momentum looks completely random right about now. Eventually, you can see how Debounce actually recognizes digits that are somewhat more complicating. For example, this 9. The rest, except for Nadum, also guess it, but yeah, this 6 really looks like a 0. It guessed this was a 6, but that's somewhat reasonable. Again, this is definitely not a 9. Alright,